Okay. Hello. Is this on?
Yeah.
Okay.
Yes.
All right. It's a pleasure to introduce Professor Hao Kuo-Chen from the Department of Geosciences at National Taiwan University. Hao has worked with us since 2014, I think, is when we started working together first. And he's been here before in 2016, I believe, the first time. Hao's going to talk to us about the recent earthquake in eastern Taiwan. We've done a lot of work in a very short period of time, thanks to their artificial intelligence, which they've also been developing, which I guess you're going to talk about as well.
Yes.
So, Hao, thank you for coming.
Okay. Thank you, Dennis, for the introduction. Hello, my name is Hao Kuo-Chen. Just call me Hao. Hao in Chinese means good. Okay, just call me Hao. Okay. Actually, this work involves so many people, like you see here. We done from after earthquake occur, we did a surface deformation measurement and also the seismicity, so on and so. That's kind of involved. This is 20 people getting here, and actually after earthquake occur, we collect data within for six days only, and we submit a paper about this one. Okay, so something like that. So for this talk, I talk about how we look for this earthquake. It's kind of very unusual earthquakes here. Probably everyone think earthquake is unusual. Okay, so let me go on for the talk. Okay, so let's first to feel the earthquake. This morning I talked with Martin. Martin want to feel the earthquake. So we right now feel earthquake with our eyes. Okay, let me see how to play with that. This is the main shot. Okay. And go for the next one. It's very cozy, comfortable right now, and later. The shaking. Okay, landslide. Wow. Okay. So I will stop here. Yeah, and let's link here so you can look at afterward. All right. So Martin, I hope you don't want to feel the earthquake like this. Okay. And actually, see, go to next. Okay. Okay. This earthquake occurred originally reported by Central Weather Bureau is kind of offshore, and the depth is around 15.5. And actually, after 1 week, the Central Weather Bureau, which is the government responsible for monitor the seismic network, they adjust the earthquake locations around depth around to 26, 24, something like that, and the epicenter moved to the on land. I say that because originally, once the people knows the earthquake occurred in offshore, they start to guess. Probably this kind belong to A4 or B4, something like that. So full of TV, different professors have different ideas about this. maybe, okay, this is kind of the A4. Okay, they will generate tsunamis over there, or this kind of boundary fault, something like that. That's happened for at least for 1 week in Taiwan. So once you turn on TV, different channels, professor tell different story about this. Okay, so that's the idea. But I think that's kind of very serious because the location is very important in Taiwan because we are very small islands, and the fault, two fault maybe just between 10 kilometer distance. So once you move to there were different faults. I will talk about this later. Okay. This right after the main shock, Nature just published the news talking about this earthquakes. As a little bit story talking about this one, and the title is "Why Scientists Won't Surprise." Actually, for me, it's kind of surprise. It's very different compared to the previous earthquake because this one, later I will show you. There's no surface rupture. We don't know where its fault is. My colleague Junyi Yan is from in Hualien, Donghua University. After earthquake occurred, you try to look around the whole area, no surface rupture, but the uplift is around 50 centimeters. It's pretty huge, and he just right on the epicenter. Okay, so that's kind of very interesting and very curious earthquake here. Okay, so before going to the main shock, probably I need to talk about a little bit tectonics in Taiwan. This is Taiwan here. From north to south, probably around 300 kilometer length, and east-west around 150 meter, 150 kilometers. Okay, the Taiwan is right between the two plate boundary. Here's the Eurasia plate, and this is the Philippine Sea plate. In the south, there's Maria Trench going south to the north and subduct to the east, and to the north, Philippine Sea plate subduct to the Eurasia plate to the north. And then right here, Taiwan is kind of in the junction from collision to subduction. Okay, so it's a very complex region. And where is the earthquake? It's right in somewhere around here. Okay, so you can imagine like kind of three-dimensional interaction with the plates. Okay, this kind of very famous picture in Taiwan. This is drawn by engineer, the French scientist. This one is showing the subduction I just mentioned. From south, there's subduction to the Eurasia plate, subduct to east, beneath the Philippine Sea plate. And to the north, this part, Philippine Sea plate subduct to north, beneath the Eurasia plate. And what happened is very complicated. Even now, if you look for literature, when you draw the cross section, they probably have 10 different versions of the profiles. Dennis probably know that better than me. Okay. So let's go to in the detail. If we would plot the cross section like this, and this is just one of the idea for the cross section here. It's published in 2022. So this is west and east, and just right now we just look for this central section for now. For west, we have the sediments and this kind of four-band fault thrust, and it's the central range, which is the metamorphic rock. And here's the Uli Bell plate boundary around here, and it's this coastal range. And the earthquake is kind of occur in this area. And as before I say, there's so many fault here within the 10 kilometer. So once you locate wrong, well, fault become here to this different fault. Okay, so you got a different idea about how this fault occurred. Okay, so we just have a big idea about this tectonic in Taiwan. If we use the surface deformation by GPS, so this is the horizontal velocity, this millimeter per year. In Taiwan, the shorter is very huge. From Philippine Sea plate to Eurasia plate is around 80 millimeter per year. And the largest displacement, the velocity changes around here, the coastal range, and something around here. This is horizontally. And how about vertically? It's very interesting. This is the mountain range, the uplift very high. And it's the coastal plain because the pumping water, so it's subsided very dramatically. And the thing we want to talk about is this area. This is the coastal range, and the plate boundary somewhere around here. We call longitudinal valley faults, somewhere around here. And we can see from south to north coastal range, this from uplift and gradual change to subsidence. That means the collision here and the gradual subsidence and subduction toward to north, something around here. So just within this 100 kilometer length, things happen a lot. Okay, so it will change to the strain rate, and the break means the concentration. So lots of concentration in the coastal range and lots of concentration in the foothill. We call foothill here. So that's we can expect the earthquake, large earthquake occur in here and also in the coastal range. So that's we have the Chi earthquake, which in the western Taiwan. The magnitude is around 7.7. And this kind of fault is kind of, we call it four band faulting structures. It's from the around 10 kilometer south to the west. And the displacement, the maximum is like 7 meters. It's pretty huge, like 3 floor high. Okay. So it's kind of, within this 25 years, it's kind of the largest earthquake occur. Okay. So let's go back to the earthquake we talked about for this topic. Okay, so this is the original report from the Central Weather Bureau. Depth is around, sorry about that is report in Chinese. The depth is around 15.5, but after they update the reports, the depth will become 22.5. And also the epicenter will move to the land. So if we plot here as a profile, or something like the hypocenter will move here to west and deeper. Okay, so that means the location is very important for the Taiwan. Okay, so after earthquake occurred, my colleague, because he stayed in Hualien, so he did a lot of survey. Only thing he can find in the harbor, that's the live oyster here. But after the earthquake occurred, the water dropped very quickly. And if we correct with the high tide, it's around 37 centimeter. And that's his kids play around in 2018. And after that, there's no water at all. Okay, so we can see the land is rising very quickly and around 50 centimeter. Okay, and then because we do a relocation and we know the epicenter of the location, and he tried to look around. There is no fault, any fault, just uplift or crack here, zoom here. So that's kind of curious. Where's the fault? Whose fault is there? Okay, and later he used the tidal gauge, try to measure any uplift. The same, it's around the 50 centimeter. So it's kind of in a same order. Also, okay, sorry about the resolution. And with the ANSAR and the GPS, all showing the same thing. It's kind of uplift, and you cannot find any fault at the surface. Okay, so it's not very usually we see in Taiwan. Okay, and this is the comparison. This is 2018. Let's make 7.4 Hualien earthquake, which occurred offshore, and then caused trigger the Million fault, and caused a lot of damage. And this kind of trigger occur here, and the uplift is around 50 centimeter. Actually, it's the same thing with the previous the 2024 this year, but this kind of can find this is related to the Million fault. Okay, and it's the outcrop and do the survey. It's all along the Million fault. So that's very, very different. Okay, and later he come up with the models. The Million 2018, the fault is kind of offshore and kind of propagate south to Hualien City, where it's here, and trigger the million fault and cause a lot of damage and lots of displacement. Okay, so that's the 2018 Hualien earthquake. But what's the happened in this event? And I think the most important, once we cannot see the force to the surface, the only thing we can do or only thing we can measure is from the seismicity. Okay, and from my lab, since 2018, we deploy the dense array around whole coastal range, and almost every year, in coastal range, there's magnitude greater than 6. For example, 2018, 6.4, 2019, 6.1, and so on. Okay, so here to 2024, that's the 7.2. Okay, and this got us the very good chance to kind of scan all the coastal range. What's happened? What's seismicity? How to respond for the active faults? And this kind, you can see the instrument kind of involved from very early on for the kind of vertical section, and right now 3 component and the more advanced instruments. Okay, and because the battery we all just record for the 1 month, and because the aftershock events kind of huge, if you based on the typical things to pick arrivals, it's impossible. For example, like this earthquake, we record for 1 month, and how many earthquakes we have? It's more than 50,000. It's kind of very incredible. If you want to use traditional things to pick arrivals, that will take like many years to accomplish that. Okay, so because of this problem, we try to use the deep learning process to pick arrival, and very successful for these 5 years, and we can see whole seismicity from south to north of the coastal range. Okay, later I will show the example. Okay, and for the deep learning, we kind of developed by our own lab. For the reason for that, because we know every year we have so many thousands events need to locate and pick. That's take a lot of effort, and I just have small lab, 3 or 4 people. You cannot do that for this kind of big test. Okay, so the reason for that, we just developed the platform we call SeisBlue. We can use offline like SeisComP or the real-time SeisComP or offline Seism dataset, and go into OrbitSpy, and this is the deep learning modules. And and for this, we can kind of change different model, because right now in lots of paper publish a different AI model or different deep learning model. We can just change this and try to test which one is best. So we can do that for different deep learning module. And then once pick the arrival, we can save in the database and do a quality check. Okay, so this kind of the platform we kind of use for real time and for the offline. Okay, and after we pick arrivals, and we can do all kinds of analysis, like the location and the magnitude, something that, and also the focal mechanism. And right now we kind of finish the focal mechanism part. For example, like this event, this Guanshan event is kind of magnitude greater than 6.8, and within like the 1 month, there more than 500 focal mechanism in this area. So we can use the AI to do that. Okay, so this is the big idea. We use the deep learning module to pick arrival, and use the associator. This how to associate event and pick arrival and the location, the events. That's the whole schedule for this one. And right now it's running very smoothly. And also we kind of push this online. We can put every hour to put on our cell phone. We can see where's locate the earthquake, how many earthquake locate. So that's in my phone now. So we have different network. We can monitor the northern Taiwan or very specific site. Okay. This is example. This is the broadband run by IES, which is the academic center, and the center is from the another government running network. So we use this as a real-time data set to my lab, and we can locate the earthquake automatically. Okay, so this is the data we have. For example, for this one, just one day we have more than 2,000 events in this area. Okay, just one day, and this is the kind of statistics value for that. Okay, and also almost every big earthquake occur, we just went out to deploy the dense array. This is a comparison. This is from broadband, like the only 14 station here, and this is the dense array we deploy like 36, and you can compare almost the same period. The event were very, very different, and this is the static calculation. This is from broadband 14 station, and this is from the smart solar dense array. It kind of lots of information get into this data set. Okay. So for 2022 making 6.9 example, this earthquake occur in the central range, which is here. And 20 years data set, this kind of almost empty. So we kind of got lucky to gather this earthquake and complete all the seismicity in eastern Taiwan. Okay, so this is kind of example to show that. And this slide is quite busy. This provide show from southern to northern Taiwan, northern coastal range. So this is the south to north. So you can see the pattern is quite interesting. For example, let me pick one. For example, like this one. This one, this coastal range and this central range. And you can see that there are two clusters. One is near vertical. We call it central range 4, and this is the coastal range longitudinal valley fault. Okay, but once you move to this is the southern part, once you move to the northern part of the coastal range, things start to change. Okay, you can see this kind of vertical here, but once you move to a northern part, it kind of vertical and become horizontal toward to the offshore. And this longitudinal fault become deeper toward to the north. Okay, so it kind of relate to the plane motion and also the fault interaction to each other. And this also will be shown in the list, the event we talked today. Okay, so this quite a very interesting event in 2022. The magnitude around 6, we call Guangfu earthquake, which is here. And as previous slide, I show in here, there's a very vertical seismicity. But once moved to the northern part, you can see the seismicity from very steep and kind of flat and toward to the offshore. Okay, so it's kind of very interesting pattern to see the change here. Okay, let's see the movie from now. There's three aftershock sequences, and we can recall. First is here, northern part, and the middle part, and the central part. And you can see the movie goes down. The seismicity kind of filling the seismic gap. It's very interesting to see the time and the space change. Okay. So this is 2021 here. The first small places. And later occurs in the central coastal range. So you can see there's kind of gap in between here. And after that, 2022. So filling the gap. So it kind of continues from here to here. Okay. It's very interesting to see that. Okay. And based on that, actually, we use the deep learning platform we can use for the 4D monitoring, and also we do the CCSI and for the geothermal energy exploration, because we can do it very quickly. Within 1 month, we can do all the analysis. Okay. And this is the event I'm talking about. Within this 6 years from 2018, there's lots of earthquake greater than 6 from northern part of coast range down to the southern part of coast range. And you see that this 2 fault system. The red colors means longitudinal fault, and the blue green colors means central range fault. And this one people think it's kind of a plate boundary fault for Eurasia plate and the Philippine Sea plate. Okay. So that's earthquake occurred a lot in eastern Taiwan. And after earthquake occurred, we kind of this is a report by Central Weather Bureau, and we did a kind of work to repeat all the location of the magnitude greater than 5. As you can see, here it's kind of very random, but once you do properly for repicking, you can see the pattern and also the fault geometry very well. Like this one, it's shorter one, and it's kind of very close and close to each other. And this is the one is the main shock. Okay, so that's very important because maybe in other place, because fault is kind of wider, if just jump around, it's fine. That's all the same fault system. But in Taiwan, maybe you will kind of just jump to another fault system if we do not locate properly. Okay, so this is the aftershock sequence after the main shock from main shock until around 24 days after that. Okay, so this is recorded by broadband station, and totally it's around 70,000 events. Okay, if we look at this statistically, main shock occur, there are lots of earthquake occur and drop very quickly. And on April 22nd, it increased very quickly and it starts to reduce the earthquake of number. And this is kind belong to kind of different fault structures. Okay, so we plot the east and west profile like a CC plot here. Okay, this is here. So just based on this, we can see there are 2 fault systems. One is here, it's near eastern, very steep vertical fault, and the other one is this one. Okay, so the first one, the main shock is very steep, deep into the east, and the second one is April 23rd. It's kind of very horizontal, kind of just above it. So like it looks like this occur first and then trigger the shallow one. Okay, so it's kind of very interesting, and it's hard to see in Taiwan somewhere. Okay, and the magnitude is complete of magnitude is around 1.2, and it's the kind of background seismicity. It kind of almost similar pattern in here or there, but we can see a clear pattern. Okay, so let's see the earthquake occurs through time. So the red one means deeper one, is very steep one, and this one caused the landslide, just we saw in the movies. So it's kind of main structure here, and on April 22nd, suddenly, last earthquake occurred here, and this is the coast range, and all the events just kind of within 10 kilometers. So it just cut through the mountains. Okay, so it's kind of very interesting to see. This is a steep one and also a shallow one. Okay, and it's the same thing. And focal mechanism show that it's all related to the thrust faulting. which is very common in this part area. Okay. If we plot the profile based on the background seismicity, we can see this is the southern part, central part, and northern part. There are two clusters. One is the sharp, very from steep dipping to the gentle dipping at the shallow part, and also the other one is the dipping to the east. Okay, so this is the around 20 years the record seismicity in this area, and this one is the record by dense array 2018 to 2022. We record by our own, and this is the dark gray, and you can see that it's very interesting. All of this aftershock sequence just above this boundary. This is the gray line. It's very interesting. Still, I need to think about why it's kind of the sharp boundary for this one. Everything occurred from 2018 to 2022. It's all kind of in the upper part of this area. And how about the main shock of this event? This in red. It's here. Actually, which is occur in the background seismicity as well. Okay. And also the other seismic pattern is something like that. And the blue stars means magnitude greater than 5. And we do the relocation on this. Okay. And so this we also plot with the tomography. And this one, this kind of very busy slide here. This is southern, central, and the north part of the coastal range. This is southern, central, and north. Okay. So the in the beginning, this is the main shock. It's occur around 15 to 35, something like that. It's dipping to dipping to the east, and then occur the shallow part, something like here. And you can see that several branch. This is the deeper part, and also some branch over here, and also part as well. And I plot with the VP tomography, the thick bright light 7.5, which represents the morehole depth, something like that. So we can see that this kind of follow the morehole depth very well around here. Okay. And we interpret this part is kind of belong to Philippine Sea Plate, and this part belong to Eurasia Plate. As I mentioned before, this is the section in southern of the coastal range, and this is the northern part of the coastal range. And you can see from southern part of the coastal range, these two faults are kind of separate. But once you move to the northern part, it kind of emerge together and it's become very busy in somewhere here. And also, there's kind of very gentle dipping to the west, and the seismic coming to the offshore, something like that. Okay. And if we look for the seismic reflection profile here, it's like the backshots to the offshore. So we can start to think about all the four geometry and the fault system in this region. Okay. So this is our interpretation. Because this earthquake belong to the plate boundary fault. So we can put a plate boundary fault here, and this is Eurasia plate. And somehow this kind of link together to the offshore, something like that. And in this area, last earthquake occurred within the Philippine Sea Plate, and this is the central range, the Taiwan orogeny here, which is not so many earthquakes occur. Okay, this relate to the reality. Okay, so that's quite interesting because we know the main shock occur first, and the triggering the shallow part later. Okay, so it's kind of the whole story for this plate, and also if we look for the Philippine Sea Plate in the southern part, it's still collide. Once it moves to the northern part, it starts to subduct to the north and also westward. Okay, so it's kind of related to the plate boundary fault, and the spline fault system. We cannot observe any rupture at surface. Okay, let me talk about the detail about the triggering fault in here. This April 22nd, we call Sophon Swarm. it's kind of very interesting swarm. Within 24 hours, there are 26 make it to the greater than 5. Like every hour, you feel the shaking a lot. Okay, and you think you are kind of dizzy. You feel kind of dizzy. That happens. So what? Yeah. Stronger. Stronger. Okay. And let's just only make it greater than 5. But there's so many earthquake occur here in this area. And you can see that this is the coastal range here. All the depths around 10, something like that. So it kind of like a knife cuts through the mountains in this area. And all the focal mechanism is all thrust faulting and with flat dipping. Okay. So later I will plot with the profile, and this is the seismic profile offshore. I will show later. Okay. So this is a static number. Within 24 hours, were around 1,300 events in here. Okay, and it's typically like the swarm nest. It's not any distinguished with the magnitude. Okay, so if we plot the profile here, we just plot C D, which is here, C profile here, and a D profile here. And if we plot the seismicity here, you can see from the central range, it's very steep, and toward to the east, very gentle, and finally maybe go out to the offshore. And also for the CC profile, you can see the same thing. And you can see another branch just coming to the surface. Okay, and this is plot with the focal mechanism. So you can see it's very shallow dipping, and it kind of propagate to the offshore. Okay. And this pre-boundary I mentioned in previous slides. This is probably related to the Philippine sea plate. Okay, and this is the model published in 2022. So this kind of form probably related to this one. It's very gentle fall and cuts through the coastal range and forward to east to offshore, and less very busy here. Longitudinal very fall and central range fall come to close to each other in here. Okay, which is kind of related to the place here, central range fall and the longitudinal valley fall here. Okay, but the question is, it kind of hard to link to with the surface active fall. For example, this Linden fall, and we cannot see kind of very clear seismicity beneath it. Okay. And we try to retrieve the old data set. This from Marcus Lenses in 2009. Let's profile here, which is here. Okay, we probably can see kind of thrust faulting somewhere around here, and there's some detachment around here. So kind of let's back thrust all the way to the offshore. And this is another profile published by John Sapit group, which is the line is farther south of the coastal range here. Probably show a similar pattern, but this profile, it's hard to see the deep reflection here. But in this profile, we probably see it's around 10 or 12 kilometer, which may be reasonable for this kind of detachment around here, this area. But that's my model for now. Okay. Okay. So this is another movie to show that. The reason I show this to me because in 2022, less Guangfu earthquake occurred in this area, suddenly stopped here, and then 2024 it continued all the way to north. Okay, so you can kind of think that it kind of relates to the time and the space evolution of the fault systems. Okay, so 2022, it kind of stopped here. And just here in 10 kilometers in this place. Okay, and wait for another 2 years. Like we see before. This running to this part. And suddenly fill a gap for this. And this kind of like the sharp boundary actually is somewhere around here. So it's kind of like move to north and somehow stop here and wait for 2 years and then rupture again and just cut through all the coastal range here. Okay. So it's kind of less more detailed research need to understand the time evolution and also the space. Okay. Okay. And this will be my next slide. This slide will be like the profile the movie from the south and gradually move to north. And this also this is the tomography. Here, the central range is here, and the coastal range is somewhere here. And you can see how it evolved with space and time. And let me take more about this. This kind of boundary for the central range, which kind of belong to the Eurasia plate, and this is the Philippine Sea plate. And here is the high velocity here. It's kind of called dense called subduction channel, flow something like that. And the earthquake just around all this subduction channel. Okay, we can see slowly. Okay. Oops. Let me stop. Okay. Sorry. It's hard to control. Okay. For example, like this one, this is the main shock. And this is the kind of plate boundary here, followed by you can see the tomography, this is the mohole somewhere here. And this is the high velocity here. And also, you can see here's kind of a gap. And once you move to a little bit northern part, this four comes kind of close together and kind of link together to the offshore, something like that. Oops. Why? Okay. And this I want to show is kind of in here, northern end. And this part is quite interesting. You can see this Philippine sea plate start to subduct westward beneath the central range. And this kind of it's very deep basin we call Herping Basin, lots of sediments. And this part is the Philippine sea plate, kind of going down and going toward to the west, not only to the north, but also the west. So you can see the plate interaction and also seismicity go with it. Okay. Okay. So I will probably stop here. Okay. Thank you. Thank you.
with 50,000 earthquakes a month, you can do some sort of ecotourism. Earthquakes,
Yeah, yeah.
pretty much guaranteed. Anyway, any questions? Mark?
Yeah. Yeah. I can take you to layer.
So you record a lot of earthquakes.
Yes.
You try to, or maybe you did it already before, to see if you can see the effects of tidal changes or for example, of weather events on the amount of earthquakes. Yeah. Because I guess, of course, with the increased water pressure, you increase probably fluid pressure, incoming water from rainfalls.
Yeah.
Increase fluid pressures.
Yeah. Okay. Good question. Actually, I just show it very briefly. How to go it? Yeah. I have slide to show that. Okay. Oh, sorry. No. Okay, this one. Oh. Oh no. How come? One more. Yes, this one. Okay. This I call 4D seismicity. We have the network in Eastern Taiwan. We call Chisang fault. It's very active fault. And we try to do the experiment from the different scale. We put a fiber, up fiber, and also the dense array and also broadband array. And this figure shows we established the network since 2021 and start to record earthquake here. Okay. And for this one is the kind of aftershock sequence without problem because it's kind of, you can see that. Most interesting is this one. This record in typhoon season. And there are 3 typhoon seasons here. And you can see once typhoon come in and the earthquake number kind of decreases a lot. But that comes with another issue is because the signal to noise too high to make this kind of low seismicity. But for now, we kind of try to analysis the signal to noise ratio, probably not affect too much. So that's probably the things we seen in here. And actually several paper published about this one. And this kind of coincidence for 3 typhoon. And the earthquake numbers drop very quickly in this area. So actually, I want to say this kind of data value is very huge. For now, we kind of just can digest for the distribution for now for 50,000 events, and later come with a lot of them announced later. Yeah, this just will happen within this by or 4 years. Yeah. Okay. Thank you.
Can the rupture be foreseen by, for instance, making some time-lapse analysis, seeing that the structure changes before the big events? Have there been studies in that direction?
No, not actually. Because most of the part we kind of tracing the aftershocks. So the events we have is kind of almost aftershock until like this one's kind of until these 3 years we start to establish the real time. And I think the data set we have right now to do the things probably not good enough to do that. I don't know, but I'm not expert on that. Yeah, probably later. Yeah.
And I guess with this activity, there is 0 silent events in Taiwan, or do you have knowledge about silent earthquakes at some places, continuation of the rupture, or is it all active as we see it here? Or
You mean a different region?
Yeah,
London earthquakes.
yeah, if you have silent earthquakes at some places in continuation,
Let's
because you're accumulating a lot of movement and
yeah, that's a really good question. Actually, we just talking Kei-Chen and her colleagues, he work on the kind of slow earthquake, something like not right in this region, but a little bit western southern part of Taiwan. Yeah, but we can look for that because we don't kind of really focus on this kind of event yet. Really, we just kind of just start to think about how it work and what kind of mechanism, something like that. Yeah, but yes, Kei-Chen, she reports some event in Western Taiwan, but here it's not so well studied yet. No, I don't think so. Right, Patty? Yeah, I really don't know actually. Yeah,
thank you.
yeah, thank you.
Anybody else? One? Thank you.
It's a very impressive catalog and tool set that you have. Are you aware of any other like super large catalogs like this one? How do they treat the data and what do they do with so many earthquakes and what are you going to be doing with all that information? Because I mean, as a data set, it looks impeccable. No, it looks like it could never be better for a geoscientist. For the community, it must be terrible to be living there. But for you, what are you planning to do with all that information?
Actually, there are lots of application later for that. First of all, I should say from our government central bureau who respond for the seismic monitoring, they cannot complete the catalog right now because after 2018, so many earthquakes occur. They just doing by hand pick it, so never keep up with the complete catalog. And lots of scientists in Taiwan right now, they still rely on this kind of catalog. So we can kind of provide the basic catalog for lots of people to doing the other application like a B value or lots of statistics analysis. And another one, I think that's very kind of important for future for work with the structural geologists, because back into maybe 5 years ago or 10 years ago, the location and the accuracy and uncertainty is pretty large. So if we want to talking about the species faults or what kind of fault system interact to each other, I think that's still the scale and the resolution is not good enough. But with this kind of the scale and resolution, and also with focal mechanism, you can see the how it link to each other and how the fault interactive. I think that's the kind of future thing we can develop for this kind of research. Yeah.
Thank you.
Thank you.
So the key to that, carrying on from Juan's question, the key to that is the development of SeisBlue and the deep learning AI, where you can pick 50,000 earthquakes a month.
Yep.
Instantly.
Maybe 10 days. Yes.
Yeah. Well, at least.
Yeah. Thank you. Yeah.
And also the accuracy in the location, I think, is very important. I mean, working with the work we did, when you have plus or minus 5 kilometers on an event, it's kind of difficult to relate it to any individual fault system. So this deep learning thing is very impressive.
Right. And later will come with the high resolution tomography. So you can see more fine scale. But the problem is we need to come out how to interpret. I think that's the things we need to come out with. Like for this 1 week, we just talk about a lot about this. Yeah. It's whole new things comes out.
Actually, I was going to ask, excuse me, on that direction. I mean, with this huge data set, have you already improved the velocity model? You are doing all the inversions?
Not yet, not yet,
Nothing.
not yet.
It's going to add, I guess, a lot of tiny giddy details on.
Yeah. So we kind of just collect the data. We kind of have a good distribution right now, so we can kind of do the next step for the tomography inversion. Yeah, the tomography inversion I show is kind of 12 years ago. It's a long time ago. It's my PhD thesis. Yeah, so we can come to the next level.
But you're moving from like a 8-kilometer grid size, now with your dense deployment and everything, and what you can go down to probably 3 or 4 kilometer.
We test probably within 1 kilometer if you're okay. Yeah.
Vastly improved resolution.
Yeah, yes, congratulations for your work and your excellent data set.
Thank you.
I just have this technical problem. What's your experience with using these smart solo devices for this kind of aftershock recording? I mean, they work are nicely to work with or not, or they make troubles with batteries and I don't know.
Yeah.
I mean,
I miss you. Sorry.
yeah, sorry. About using these smart solo devices
Yeah.
for aftershocks, did you feel that it's a good tool, that they work fine, or yeah?
Yeah. Okay, thank you. I think that kind of is kind of good chance for us, to do the fine resolution, because in the end, like Rama asked the question, we want to have the high resolution tomography as a final product. So once you have the dense array, so it's kind of
Can you go back to, you put up a chart where you evolved over time the instruments that you used, et cetera,
oops.
right at the beginning of your talk,
Right on the very first.
Yeah, all right.
right at the beginning.
Mhm. Yeah, okay. I'm going wrong direction. Come on. Oops. Okay.
You're going.
Sorry about. Okay, right direction now. Okay.
Here. So I guess Jordy is asking, do you find this smart solo instrument better than the?
Oh, okay.
Et cetera, et cetera.
Okay, thank you. Question. Actually, for this involved, because for early on it's only vertical. The vertical means the things we can pick almost just P wave. So involved for 3 components, we can have the beta S wave, but from here to here it's kind of huge difference. Consider the funding and the money. This one is kind of very expensive for the original, and this one is kind of cheaper. And compare the quality. This one's much better. Consider the signal to noise ratio we can test, and for the charge and how to download data, this one is much easier. So consider all of the aspects. This much better. Yeah. Hopefully this kind of answer your questions. Yeah. Okay.
And they have a deployment life of whatever that means to change the battery or what, about a month or?
Actually, it can depend. This battery is here. Let me see here, and the battery can last 1 month to 3 months, or you can put a solar panel. So it depends on what kind of purpose you want to use. So it kind of adjustable for that. Yeah. But for us, kind of 1 month will be good enough to record aftershocks already. Yeah.
How big is it? Can you say? It's small. Oh, that's okay.
It's very small.
Then how can you how can you attach a solar panel to that device?
What?
is not possible, or is it possible to install a solar panel with the smart solos?
Actually, you need to change the battery side. There is kind of connection outside for that. Yeah.
I didn't know that. Thank you.
Yeah. And actually kind of friendly. Actually, you can ask for what you need, and then you can adjust for you somehow.
One last from my part. You keep the time and you keep the waveforms?
Yes.
Wow. That's a huge storage.
Yeah. So I don't have the PDD for that. It's kind of like 10 or some terabyte, something like that. Yeah, terabyte. Yeah. So lots of things to digest. Actually, we just kind of maybe 1/10 or it's 1/10 of analysis right now. Yeah.
And you just run this size blue on an ordinary computer or a supercomputer, or how do you run it?
We have small server. Actually, it's not kind of very high demanded for the server. We just very small workstation will work fine. Yeah. And by the way, the waveform training is based on our own, because we spend like the 2 or 3, 4 years to pick arrivals. So that's take time too. And then training to the models is all our own and belong to, I should say, kind of fit to the Taiwan models. So it can kind of better because it changed a lot. If you play with the other transformer or something, because they use different data set, it's kind of maybe belong to like California or something like that. And you want to train your model or predict your earthquake in Taiwan, they will have some lost. Yeah, so I believe.
There's a regular human supervision to the entire system.
Yes. And actually, every earthquake here, we put a QC. We visualize every event. So, for example, 40,000 event, we look everyone for that. Yeah. So we can make sure that's the events. Actually, two people looking for these events.
One question here.
Yeah.
Thank you for your presentation. Do you feel able of predicting the location of the next swarms? For me, it seems that it's migrating northward, right?
Yeah.
So
Yes.
are you expecting the next big earthquake trigger swarms in the north?
For that shallow one, probably maybe too offshore. But
Sure.
from my perspective, maybe because let me show. That one is very interesting, and Dennis and I talk a lot about this and a different idea about this. This one. They want to show. Okay. Sorry. Okay, this one. So this event, like I showed probably in the movies, originally it's 2022. It's occurred in this area, and it stopped somewhere around here. And in 2024, which is this year, it start to occur again, propagate to here. Yeah. So probably I think the shallow part will be or we need to aware of this propagate to offshore because it's kind of very shallow, and if it does, it will cause a rupture and maybe some kind of tsunami or something like that. That will be very dangerous for this one. Yeah. And actually, originally, for my earliest talk, people kind of think this kind of main shocks is this one. So they kind of aware of maybe cause a tsunami or something offshore rupture. So lots of people go out to do a research, deploy OBS, deploy lots of things on offshore. Yeah. Okay.
Anybody else?
You have a lot of earthquakes offshore, which is the confidence of the depth of these earthquakes, because you don't have OBSs on this area, no? And you have at least 180 degrees of azimuthal coverage. So are you confident with the depths of these earthquakes? Or?
Oh, yeah. That's very good questions. Actually, for us, we need OBS for sure. So that's we kind of see there's all the big S mass we constrain more than 180 degree for that. So actually we call lots of events here, and we show lots of events, but the residual and the text uncertainty are huge. So we just remove it. So we only constrain the uncertainty within 10 kilometers. Will kind of get into our plot and our catalog. Other than that, we just destroy it. Although it's lots of events, but we still destroy it. Just putting aside, not putting here. Yeah. So we have a lot of constraint. First, we check by our eyes, and then we check by statistics the uncertainty, maybe within the 10 kilometer or residual, which what certain threshold, and just put into our catalog and do a relocation. Yeah. Thank you.
Are there stations on Okinawa somewhere you can use?
Yeah. There's some from Japan, but pretty far away, actually.
Yeah.
Pretty far away. Yeah. And actually, there's cables run by Central Weather Bureau, which is government, and we look for it because the couple is not so good. So even for the main shock, it's hard to identify the first break, even. So it's kind of hard to use that. Yeah, because right.
Do they have the OBS cable?
Yeah. They also in the north south actually, and northwest. There's three stations, I believe. More than 3. Yeah. Okay. Yeah. Yeah, and I look for 3 stations. It's kind of pretty noisy. Right? Probably that was something happened in OBS actually. Yeah. Because of the coupling.
Very long cable with,
Yes.
I don't know how many OBS is on it. I can't remember.
Yeah, but some are broken and some from the Central Bureau actually. Yeah, kind of around the Taiwan actually, but the kind of working probably just say working.
No,
Mm-hmm.
so the sensor is comes with the cable, so it's not covered so well. So
Yeah.
I think that's the reason that he said that you're gonna clear.
Yeah.
Clear.
Pretty waveform.
Okay, anybody else? All right, yeah, thank you very much.
Thank you.